6.2 Logarithmic Functions and Equations. So today we're going to be talking about something a little bit different. Last time in 6.1 we introduced exponential functions and equations, which was a lot different than what we're used to. And today we're going to introduce our log functions. So, defining the log function. The inverse of the exponential function is actually the log function. I'm saying log instead of logarithmic function, just a pretty standard shortening that people use. In general, log functions have this form. F of x is equal to, and I'm going to read this a certain way, log base a of x. And just like I said in the notation here, we say a is the base of my logarithm. So again, this is the inverse of the exponential function. Remember that we have exponential functions. These are functions that have the form f of x is equal to a to the x. Well, since the exponential function and the log function are inverses of each other, we know from our inverse function section that if I compose these two functions, then I should end up with just x. So more importantly, why do we care about our log functions? Well, to understand this, we first must understand the relationship between the log and the exponential, or how to convert between them. In general, if I have the form a to the y power is equal to x, then I'm allowed to write log base a of x is equal to y. If I have a to the y is equal to x, we call this our exponential form. If we have log base a of x is equal to y, we call this the log form or logarithmic form. So we're going to go ahead and do a little bit of practice between this conversion. For example 1, write the following equations in log form. For the first one, I have 2 cubed is equal to 8. Again, I'm not solving for anything. I'm just rewriting and converting this into a new form. Well, I know if I have a to the y is equal to x, then log base a of x is equal to y. That's what I just had in this beginning part. So I want this to look like log base something is equal to something. Well, the way that I like to remember this is that, remember in our exponential function, I called 2 to be my base of the exponential. For my logarithm, whatever my base is of the exponential, that's also the log of my base. In other words, if I'm comparing my two forms, my a, in this case, is 2. So I have log base a or log base 2. Continuing from there, my power in my exponential should end up being by itself in my log function. So in this case, 3 is my power, so that's going to go by itself. And then whatever is left over, that's going to go inside of my logarithm. So in this case, my 8 is my x from my original conversion. So I've rewritten this in logarithmic form. We're not doing anything else from this point. I'm simply converting it to a logarithmic form. Let's go ahead and try part B. For part B, I have the square root of 9 is equal to 3. This might look a little weird because I don't have any power, but we actually do. We do have an exponent. I can write this as 9 to the 1/2 power is equal to 3. Remember, a square root is equivalent to writing an exponent of 1/2. Well, now if I look at 9 to the 1/2 power is equal to 3, I can change this into a logarithmic form. That is, I can write this as log with the same base. In my exponential equation, 9 is my base, so that's the base of my logarithm. The power, we said, goes by itself. And we have our leftover of the 3. So if I want to rewrite log of 9 to the 1/2 power is equal to 3, this is equivalent to log base 9 of 3 is equal to 1/2. So we have this here. For part C, we have 7 to the negative second power is equal to 1 over 49. Note that my logarithm still does work out even if I have a negative power. Again, I can write this as log with the same base. In this case, I have base 7. Inside my logarithm goes 1 over 49. And on the right, I should have my power. So I have my 3 equations in logarithmic form. It does take some practice and getting used to and rewriting this log form, especially if you're not familiar or you haven't seen logarithms before. So we have example 1. Now let's look at example 2. This time I have it in logarithmic form. Can you write it in exponential form? So for part A, I have log base 8 of 64 is equal to 2. Once again, I like identifying my base. Here I have log base 8. So I know it should be 8 to some power. Well, remember, whatever was by itself in my logarithm, that's going to become my power, and I'm left with 8 squared is equal to 64. Another way that you could have remembered this is, what if you accidentally mixed up your numbers? What if you said, all right, we have 8 as our base, where does 2 and 64 go? Well, if you accidentally mixed it up, then you would have written 8 to the 64th power is equal to 2, which doesn't make much sense for us. That's clearly not true. Remember that whenever we write this in exponential form, it should still make sense and be true. So, I have my first exponential form. Now we can continue for the other parts. Part B, once again, I like identifying the base, 64. And then between 8 and 1/2, I have to see which one is my power. There's multiple ways we can look at this. I can either remember my conversion or some other type of pattern, but I should get 64 to the 1/2 power is equal to 8. Again, if you accidentally mix this up and you accidentally put 64 to the 8th power, that's definitely not 1/2. So I have my second solution. Again, I'm leaving it in this exponential form. Can we simplify it? Then yeah, but we're leaving it in its standard exponential form. Now for my last part, 1C, identifying the base of 5. Whatever is by itself, we get as the power. And whatever is inside the logarithm, I leave it on the right, giving me 5 to the negative 3rd power. That should be 1 over 125, which does turn out to be true for us. So make sure you do some practice on converting between these two forms. All right, so now that we have some practice with converting between exponential and logarithmic form, let's go ahead and introduce another definition. My next definition says, if the base of my logarithm is 10, we actually call it the common logarithm. That is, whenever I have log base 10 of x, we can actually often write it as log of x. In other words, there's an understood 10 if you don't see a base here. So we have our common logarithm. Now, if the base of my logarithm is e, remember e is a special number, it's approximately 2.718, something like that, then we actually call it the natural logarithm. In other words, whenever I have log base e of x, we just write it as ln of x. The reason that we have these two notations is that the common logarithm and the natural logarithm often come up in many applications. So we have the definition of the common and natural logarithm. Now, I want to introduce some common properties of the logarithm. Here I'm going to call them basic properties because we will be discussing other properties in the next couple of sections. So, first off, for any logarithm, I'm looking at this first column here. If I have log base a of 1, that is always equal to 0. In other words, if you do log of 1, no matter what the base is, we should get 0 no matter what. If I do log base a of a, in other words, if my base matches what's inside my logarithm, we get 1. You can see on the right, if I go to the middle column, if I do log of 10, remember, if I don't see a base that's assumed to be base 10, so in my second column, I'm saying log base 10 of 10 is also equal to 1. My base was equal to whatever was inside my logarithm. And the same thing for the natural logarithm as well. For my third row, if I do log base a of a to the x power, then I just get x. In other words, if my base matches what's inside my logarithm to a power, then that simplifies to the power. So you can see the same thing again happens with the common and natural logarithm. And then if I do a to the log base a of x, I also get x. And if I do an analogous argument, 10 to the log of x, we get x. And e to the ln of x is equal to x. So these are some common rules that we're going to use to help us solve some log equations or simplify. So let's go ahead and do a couple of examples involving these basic properties. For example 3, evaluate the following expressions. So for part A, I have log of 100. If you want, you can go ahead and rewrite this as log base 10 of 100. Again, if there is no base, there is an understood base 10. All right, so how do we work through this? Well, remember, we have a property that says if my base matches what's inside my logarithm, then I'm able to simplify. Well, in this case, one thing I may notice is that 100 is the same thing as 10 squared. Well, now I have log base 10 of 10 squared. Using this idea, one notation or unique thing I like to write is that here my log 10 cancels with this 10. And this leaves me with power 2, giving me my final answer. So again, I'm trying to match the same base. For part B, we have the natural log of 1 over e cubed. Once again, it may be useful for me to rewrite this. I know that a natural log is essentially log base e, but what about 1 over e cubed? Well, this can be rewritten using the property of exponents as e to the negative third power. So e to the negative third is the same thing as 1 over e cubed. Well, in this case, my natural log and my e will cancel each other out, leaving me with a negative 3, the power. This is again because a natural log has log base e. So for part C, we're pretty much going to do the same idea. I have log base 3 of 27, which can be rewritten as log base 3 of 27 with a base of 3. We can write 27 as 3 to the third power. Now if I simplify this, again my bases match. I have base 3 and the base 3 for my exponential portion, leaving me with 3. So I have my final answer for this first row. Now we continue forth into the second row. 4 to the log base 4 of 7. Again, we have this little unique property where if I have that my bases match, in this case 4 and 4 are my bases, then I can simplify this to be whatever is left over in my logarithm. In other words, I get 7. For part E, I have log base 2 of 2 times the square root of 2. This might look a little weird at first, and we do have to be careful here. Right now, we don't have the same base. We're almost there. Because whatever is inside of my log here, it's not just a plain 2, or nor a 2 to a power. It's 2 times the square root of 2. However, I could rewrite this as log base 2 of 2 to the 3/2 power. Now, how did I get 3/2 as my power? Well, I'm going to do this work on the side. How did I know that 2 times the square root of 2 gives me 2 to the 3/2 power? Well, 2 is like 2 to the 1 power. Square root of 2 is the same thing as 2 to the 1/2 power. So whenever I multiply these, it's just adding the exponents. So 1 plus 1/2, I get 3/2. So that's how I'm changing 2 times the square root of 2 into the form 2 to the 3/2 power. And once again, by doing this, I can very conveniently cancel out my bases. That is, my log base 2 can cancel with my base 2 over here, leaving me with 3/2 as my power. And then for part F, I have log of 1, 2, 3, 4, 5 of 1. Well, in this case, remember, if I ever do log of 1, natural log of 1, whatever base of 1, this will be 0 always. So it doesn't matter what my base was. What mattered was I did log of 1, which is always 0. So we have example 3. Now, looking at example 4, we're just going to get a lot of practice in. Solve the following equations. We know how to simplify some log expressions, but how do I solve a log equation? For part A, I have log base 2 of 16 to the x power is equal to 5. So there are two ways that we can actually approach this part A. One way is if I go all the way back to my beginning, where I convert it between log and exponential form, I could use this conversion to rewrite my expression. That is, if I write this in exponential form, then I can write this as 2 to the 5th power is equal to 16 to the x. Again, this is my conversion between logarithmic form and exponential form. If I do it in this way, then on the left, 2 to the 5th power, what does that give us? That gives us 32, equal to 16 to the x. You might be looking at this and saying, wow, what do I even do with this? I propose that we do it a slightly different way. I wanted to show that if you get tempted to do 2 to the 5th, then we get a little bit lost here. To solve this exponential equation, remember that I could try to get the same base on the left and the right. On the left, I have 2 to the 5th. On the right, 16. I can write 16 as, well, 2 to the what power? We can write as 2 to the 4th power to the x, which then may be written as 2 to the 5th is equal to 2 to the 4x power. And then I now have matching bases. Since my bases match, I can go ahead and just look at my exponents, leaving me with 5 is equal to 4x. Or if I just divide by 4, I get x is 5/4. This is one way I may approach it. So what's the other way that I can approach this? The other way I might approach this is going ahead and using my properties of the logarithm. So let me go ahead and draw a dividing line to show that this is our second way of dealing with it. So if I look at my log equation, I might recognize that 16 can be written as a base of 2. That is, I could write this as log base 2 of 16 is 2 to the 4th to the x power is equal to 5. So I have the same equation, which if I clean it up a little bit, gives me 2 to the 4x power is equal to 5. Well, if I use my properties of the logarithm, I notice here my bases match each other. I have log base 2 and 2 to the 4x. Using this, I can go ahead and cancel my bases, giving me 4x is equal to 5, which will lead me back to my previous solution. So we have two ways on which we can solve this problem. Now let's look at part B. I have 7 to the log base 2 of x is equal to 49. Well, this is overall an exponential equation. Right now I can't do any cancellation. However, one thing I might notice is that on the left I have a base of 7, and on the right I can write 49 as 7 squared. In other words, I could match my bases. If I match my bases, that means I can set my powers equal to each other, giving me log base 2 of x is equal to 2. And now I gotta figure out, how do I go from here? Well, since I have a log equation, I can go ahead and convert this to exponential form. So if I convert this to exponential form like what we did at the beginning, I can get 2 to the 2nd power is equal to x. Or in other words, x is equal to 4. Again, I'm using the properties of my logarithm, where I convert it between exponential and logarithmic form, or my properties where I can cancel out using a common base. So we have example 4. Now we can look at example 5. Example 5 says, solve the following equations. Part A, I have log of 4x is equal to 1.8. So, again, one way I can do this is, well, before I do that, notice that there is no base on this logarithm. So if you want, you can write log base 10. We haven't understood base 10. So, I could do this, again, one of two ways that will lead me to the same answer. The first way is converting to exponential form. If I convert this to exponential form, I can write this as 10 to the 1.8 is equal to 4x. So that's one way I can do it, by directly converting through what I know about an exponential equation. The second way I can do this, I'm going to go ahead and write the second way to start off, because you'll see that we actually get the same equation in any case. So let me rewrite this. Log base 10 of 4x is equal to 1.8. Another way that you could look at this is, remember, if I do one thing to the left side, I have to do it to the right side to maintain equality. So for this one, I could also do, what if I make both sides a power with a base of 10? In other words, what if I make the left 10 to the power of log base 10 of 4x equal to 10 to the 1.8 power? The reason I might be interested in this is on the left, I have a common base of 10 and 10, which is allowed to cancel out by my properties of the logarithm, giving me 4x. And on the right, I have 10 to the 1.8 power, which is exactly what I had on the left side. So in either case, I get the same equation. The second method is something a little bit new that I'm introducing, but it's still based in the same idea. So now, since we have the same equation, I'm just going to solve for one of these equations because we're at the exact same point here. So if I want to solve for x, I can just divide by 4, giving me x is equal to 10 to the 1.8 over 4, which approximately, let's see what we get there. 10 to the 1.8 divided by 4. We get about 15.77. And so that finishes up my part A. This time I get allowed a decimal answer because we started off with a decimal. So now let's go ahead and do our last example for today. We have e to the 3x is equal to 10. How do I even deal with this? Well, now I'm going to use a similar property to what I used in my second method for part A. So somehow I need to get rid of this e before I can get to the 3x. Usually we would get the same power and work from there, but on the left I have base e, and on the right I have, well, base 10. There's not much I can do. However, remember again, if I do it to the left, I can do it to the right. Meaning, what if I do the natural log of the left side and the natural log of the right side? If I do this on the left, natural log of e cancels out, leaving me with 3x is equal to the natural log of 10. I'm not too worried about the natural log of 10 because that's still just a number. Granted, not a very clean number, but it's a number. Now all I have to do is divide by 3, leaving me with x is equal to the natural log of 10 over 3 as our exact answer. Now I'll take this as my final answer. And so we're done with this example and this video.